There's a simple yes or no question that no computer, not today's, not $1 trillion supercomputer in the year 3000, can ever answer. And here's the twist, a man proved it was impossible before a single computer even existed.
Okay, that sounds like a bold claim. We're not talking about too hard or too slow. You mean genuinely, mathematically impossible? Like, forever?
Forever. And the question itself is almost insultingly simple. Point at any program, feed it any input, and ask, will this program eventually stop running, or will it loop forever? That's it. Does it finish?
Hold on, that seems easy. If I write a loop that counts to 10, obviously it stops. If I write, while true, do nothing, obviously it never stops. Where's the impossible part?
Right, the easy cases are easy. The problem is building one machine that answers correctly for every possible program. And to see why that breaks, let's tell this like a detective story. Enter Alan Turing, 1936.
1936, there are no laptops, no phones, barely any electronic computers at all. So what is Turing even reasoning about?
He invented an imaginary machine on paper, a device that reads symbols, follows rules, and computes anything computable. We now call it a Turing machine. It's the mathematical blueprint of every computer that would ever be built.
So he defined computer before the hardware caught up. And then he asked what such a machine could never do. Alright, let's build our detective.
Let's imagine the dream tool. Every developer wants it. We'll call it the Oracle. You give the Oracle any program and its input, and it always answers, quickly and correctly, halts, or loops forever. No crashes, no guessing.
That would be incredible. That's the ultimate bug detector. No more programs freezing, no more infinite loops shipping to production. So let's just assume the Oracle exists and see where it leads.
Exactly the strategy. In a good detective story, you follow the suspect's logic until it contradicts itself. So we assume the Oracle is real and perfect, and then we get a little mischievous.
Mischievous how? What do we do with it?
We build a second program using the Oracle inside it. Let's call it the Troublemaker. The Troublemaker takes a program, and secretly asks the Oracle, hey, if this program were run on itself, would it halt?
Run a program on itself? That's weird, but sure, a program is just text, and text can be fed as input. So the Oracle gives an answer. Then what does the Troublemaker do with it?
Here's the twist. The Troublemaker does the exact opposite of the Oracle's answer. If the Oracle says, this halts, the Troublemaker deliberately loops forever. If the Oracle says, this loops forever, the Troublemaker immediately stops.
So it's a contrarian. Whatever it's told will happen, it does the reverse. That feels harmless, almost silly. Why is that dangerous?
Because now we ask the killer question. Take the Troublemaker, and feed the Troublemaker to itself. What does it do? Follow the logic carefully, because this is where everything shatters.
Okay. Suppose the Oracle predicts the Troublemaker halts on itself. But by design, when the Oracle says halts, the Troublemaker loops forever instead. So the prediction is wrong.
Right. And flip it, suppose the Oracle predicts it loops forever. Then by design, the Troublemaker immediately halts. Wrong again. Whatever the Oracle says, the answer is guaranteed false.
There it is. The Oracle is defined as always correct, but we just built a program where it's always wrong. That's a flat contradiction. And in logic, a contradiction means one of your assumptions was a lie.
And the only assumption we made was that the oracle exists. So the oracle can't exist. Case closed. The perfect halt detector is mathematically impossible.
It's the same trick behind "this sentence is false," self-reference eating itself. Turing just turned that ancient paradox into a hard limit on computation. Beautiful and a little terrifying.
But let's be precise, because people misread this. It doesn't mean we can never tell if any program halts. Tons of programs are easy to analyze. It means no single method works for all programs.
That distinction matters everywhere. This isn't abstract math trivia, it's baked into the tools you open every single day. Take your compiler.
When your IDE says, "This code might be unreachable," or "possible infinite loop," notice the word might. It can't be certain, the halting problem forbids certainty. So it plays it safe with warnings.
Same story with antivirus software. You'd love a scanner that perfectly decides, will this file ever do something malicious? But that's a halting style question, so it's undecidable. Antivirus uses signatures and guesses instead of proof.
And it's why perfect bug detection will never exist. Tools like static analyzers must choose, either miss some bugs, or raise false alarms. They literally cannot be perfect and complete at once. That's not lazy engineering, it's a law.
Which reframes how we should feel about it. Turing didn't just find a limit, he mapped the exact border between what machines can and can't do. Knowing where the wall is its own kind of power.
So the next time your editor throws a fuzzy, maybe, warning, don't be annoyed. That hedge is a 90-year-old proof whispering that some questions have no clean answer, and never will.